So welcome back students. In this video we are going to talk about a de Broglie hypothesis and Davisson-Germer experiment. So earlier we have learned about the particle aspect of radiation, how the radiation can be thought of also as particle and explain some kind of quantum phenomena like the black body radiation, photoelectric effect, all these things. And but it is interesting to see that the de Broglie also thought that if we can think of radiation or the light as made of corpuscular particles, then this would be applicable to all matter. Like nature is not likes to be behave in that way. He thought that the all matter also can be thought of as made of waves. So if we can think of waves as a particle, then we should also be thinking of particles as waves. So he thought that the matter also should have an associated wave with it, and he said that the photon, like photon, we have considered it as a particle. We can consider the matter also as a wave with a wavelength of h by p. This is the wavelength of the matter wave, and with a momentum p by h cut. So it's with a wave vector of k. So if the matter wave is thought of as a wavelength of lambda and with a wave vector k, and matter wave is actually collection of waves. Matter wave can be thought of as collection of waves, and it should have this lambda and this momentum. So he thought like that. So that's why it's a hypothesis. Now next came this Davisson and Germer, and they conducted an experiment, and the experiment actually looks something like this. So this is an emitter and this is an detector. This angle is phi, whereas this angle is theta by 2. Okay, so what is happening? It's a nickel. So they take a sample of nickel and they are simply sending some electron on the surface of it, and the electrons get reflected, and it is again collected by some detector, which is put symmetrically with this emitter. So the angle between the detector and the emitter is theta, and the angle made with the reflection plane with the emitted electrons and the reflection plane are phi. So this is what the experimental construction is simply, and we are specifically sending 54 electron volt electrons, mono energetic. So this is the kinetic energy. Okay, this is the kinetic energy of the electron, and we are sending this electron beam, and then it is getting reflected and then detected. Now we expect what will happen. Now the electron should haphazardly scatter and go in any direction. That's if it is like a particle, then it should behave like that. But interestingly, they found that this angle theta is 35 degree. When the angle is 35 degree, then the intensity of the reflected electron beam is minimum, and when the theta is 50 degree, then the intensity of the reflected electron beam is maximum. So it is certainly behaving like a wave, similar to the Bragg X-ray diffraction. Similar to the Bragg X-ray diffraction, it is behaving as if wave, and it is giving an intensity of minimum at this angle and intensity of maximum at this angle. So that was very interesting. So if it is working similar to the Bragg X-ray diffraction, then we must be applying the Bragg rule here, which is nothing but n lambda equal to 2d phi, actually 2d sine phi. So, and they found if we take the first excitation, that is n equal to 1, for that this lambda will be 2d sine phi, and this phi is nothing but actually 2 phi plus theta is pi. So this is 2d cos theta by 2, because theta phi is nothing but pi by 2 minus theta by 2. If we put it here, then 2d cos theta by 2. So if and this theta, we know this 35 degree and 50 degree. So if we put this angle, and we can find this lambda by putting this theta angle. We know the d for nickel, the spacing between the reflection planes. So this d we know for this material, and this angle also we can measure. So from that we can find a lambda, right? Because if we know d and if we know theta we know, because we know the angle between this emitter and detector, we can find a lambda from this Bragg relation, and which considers the electrons, emitted electrons, to be waves, right? And they found 0.165 nanometer by putting all the relevant values here. They found this. And then next what they did, they calculated this lambda again using h by p that we already have seen here in de Broglie hypothesis. And this h is by p is nothing but 2 me k, right? Because p square by 2m is equal to k, and this k is nothing but our 54 electron volt, and we know the rest mass of the electron. So by putting it here, every parameters, by putting it here also, we get 0.167 nanometer, which is in excellent agreement, we can say, with our theoretical finding. So this is our theoretical finding, and this is our experimental finding, and they both matches perfectly. So we can say that our de Broglie hypothesis is indeed matching with our Davisson-Germer experiment. So we can think of the electron as a wave also, and this can be written actually psi of r and t a e to the power k dot r minus omega t, or we can write it also like p dot r minus et by h cut, which is a wave equation. And Schrödinger, actually inspired from this hypothesis, he devised his famous wave mechanics, where we always considered the electrons to be as a wave. He devised his famous wave mechanics depending upon this wave function of these electrons, and that gives perfect experimental confirmation of this is proved. I mean, it can be used in, wave mechanics has been successful in explaining many experimental observations. So this is it, how we have understood how the de Broglie hypothesis considered the reverse. Here we are considering the wave aspect of the particles. So in quantum mechanics, there is no particle, there is no wave, there is always a dual nature. It's sometimes behaving as a particle, it's sometimes behaving as a wave, depending upon the situation and the experimental setups. So that's the bizarreness of quantum mechanics. It's not always like in classical world the waves are always like waves and the particles are always like particles, but it's not like that. So that is the bizarreness of quantum mechanics. So I hope this is clear, and we will meet in the next video.